Hello everyone, welcome you all to AI Ki Pathsala. I am your host Anu, and the next concept we will learn is the concept of mean, variance and standard deviation. So these are very simple terms which you might have already encountered in your probability course or in the 12th grade. So these are very simple concepts. Let's understand what they mean intuitively and where they fail. Why are they useful and things like that. So first of all, let's understand what is a mean. So for understanding the mean, what I'm doing, let me open my notepad. So let's take your Setosa petal length, right? So here I'm taking Setosa petal length. Fine. We know that in the Setosa petal length, we have 50 observations. So let's call them x1, comma x2, comma x3, so and so forth till x50. These are my 50 observations. Now, I'm calling this Setosa petal length here, giving it name, and it's a set of 50 observations here, n is equal to 50. We already know this. So what is the mean of all of them? So mean is often written with a Greek alphabet, which is called mu. It is represented like this, mu. So mu of Setosa petal length, mu of Setosa petal length is equal to, if I will do, what I will do is the mu of Setosa petal length is the sum of x1 plus x2 plus x3 so forth till xn or till x50 or xn, whatever you say, divided by the number of values or number of observations. Let's say n. x1 plus x2 plus x3 till xn divided by n. And I know my n is 50 here. So, because you have 50 observation here, that's why I have divided it by n, where n is equal to 50. More mathematically or more concisely, you can write this as summation of, you can write this mean as is equal to summation of I is equal to 1 till n xi into 1 by n. Fine. So this is what mean means. Mean is basically your simple average, right? Now you might ask me, what is the use of mean? Why are we learning about the mean here? So what I have done here, let's write some code to calculate the mean here, and then we will discuss something further. Let's write a code. Let's first write a print statement, print, and let's say I want to print this thing first, mean. Fine. And then this thing. From the next line, let's start writing my actual code. I'm writing here print. Inside this print statement, what I'm writing, np dot mean, thereafter iris Setosa, iris underscore Setosa. Fine. Thereafter petal length. Let's pass petal length inside this iris Setosa flower. And thereafter, let's close this bracket. So this is the mean for iris Setosa. I'm just copying this line of code and pasting it here. I'm copying this line of code. Let's copy this line of code and paste it here. And simply I'm going to change iris Setosa to iris versicolor. Iris versicolor. Thereafter, again I'm copying this code And this time I am changing this Setosa to Iris virginica. Let's write virginica here. Fine. So, and for every 3 flowers, Setosa, versicolor and virginica, I am passing the petal length and I am calculating the mean by using this numpy np dot mean here. So I am getting the mean of all these 3s here. So now, just by looking at the means, by just looking at these 3 numbers here, no plot, nothing, I can quickly tell you that Setosa typically have a small petal length, while the petal lengths of versicolor and virginica are closer. So by just looking at these 3 numbers, I can tell you that Setosa flowers tend to have much smaller petal length. The Setosa flowers tend to have much smaller petal length as compared to versicolor and virginica. Of course, the petal length of versicolor typically on an average are smaller than the petal length of virginica, but the difference is not as significant as with Setosa. That's the first takeaway. This is clear on what a mean is. But I have one problem with mean. So for example, I have 50 values here. I have 50 values here and I have calculated the mean of 50 values, right? For Setosa, let's take all of your Setosa value. And we know that the Setosa values lies between 1 and 2. We know that the Setosa lies between 1 and 2. If I will just write it, I know this from my previous knowledge that my Setosa lies between 1 and 2. And the central value or the mean value is around, for Setosa, it's around 1.464. 1.464. This is the central or the mean value for Setosa. Now, let's assume somebody did one more reading. That is, somebody took this is the 50 reading. Right now I have 50 reading, and somebody take the 51st or 51st flower. Somebody introduce the 51st flower or take the 51st reading. That is one more reading. And for the 51st flower, they have mistakenly entered the number as 50. The petal length, that is, they have mistakenly entered the petal length as 50, which is like a very large, it's like a crazy, which is like a crazy high. Because 50 centimeter petal length is like a massive sized flower, right? Suppose this error happened because somebody entered a wrong number or the data got corrupted. Because we know that my 50 observation of Setosa lies between this interval 1 and 2. So 50 values are lying between these intervals, but someone has mistakenly taken the 51st reading as the value 50. So such data point is called an outlier. So it is lying between, let's say, 1 and 2, and let's say outlier is lying with somewhere here, which is like 50. Somewhere here, which is far from this 1 and 2. So such a point is called an outlier. Why it is called an outlier? Because it is not a normal. it is not normal to find a value like this 50. And this error could have happened because of many reasons. It could be because somebody entered a wrong value. Maybe data got corrupted. Or somebody, instead of putting numbers in centimeters, they put in millimeters. Hundreds of other things may happen because of this, right? So no, I have one error like this. So what happened? What will happen to my mean? So let's understand. Let me make some changes in this already written code here. So to see what is how my mean is getting affected by such error. Fine. So I'm writing what I'm doing here. I'm just copying this entire code. Just copy this entire code, paste it here, pasting it here. And what I'm doing, simply, this is, let's say, my original mean for petal length. Let's say this is my original mean for petal length. Fine. I'm writing one more print statement here. So this is the original mean of iris setosa flower. And here, let's say I have given one more value. So let's append one more value inside this. So how I can do this? np dot mean. After inside this, I'm appending one more value, np dot append, and then take iris setosa. And after this, let's write 50 here. And then close this thing. Then I'm saving this entire code. And let's rerun this code and see what I'm getting right now. So see what is happening. So if you look at this second line, what I'm doing here, I'm just taking the mean. I'm just taking this mean. If you look at this line, I'm just taking this mean by appending a value of 50. So I have 51 values here. Earlier, I was having a 50 values. Now I'm having a 51 values after appending one value. So I have my x1 to x50, and my 51st value is 50 itself. Fine. So this is one thing that you have understood. Now, when I append such a value, the mean of this is 2.4. Earlier, my mean was 1.464, 1.464. Now, if you see, my mean gets shifted here to something. You see, my mean gets shifted to somewhere here, 2.415. 2.4115. This is my new mean. Fine. Which means one simple number by one simple error could corrupt my mean a lot. My actual mean is 1.464. This is a problem because if you have one mistake or one error or one outlier, your whole mean could jump drastically. It's simply my mean. If you look, my mean just got doubled here. Fine. And this means tells you nothing because 50 points are lying here, right? Only one point lies here. So this 1 point has corrupted my mean drastically. Mean is nothing but, I've already told you, summation of all the numbers divided by. And this is what the mean is, right? And this sum could be extremely large if I have one extreme point, right? Let's assume all my flowers lies between 1 and 2. but one number exists which is extremely large. Let's say one number is 1000. All my flowers lying between 1 and 2, and one number is this, which is which has a value of 1000. So my sum will increase drastically because of one mistake. So mean has this fundamental problem that because of one outlier or one error, your mean can increase drastically. That's something that we have to take care of. And that's important because we will revisit this problem with mean and come up with new ways of measuring using things like median, percentiles, etc., etc. So having understood what mean is, so what mean is telling us? Mean is basically telling us the central tendency. And if you see here, one thing, my simple mean means summation of, I have written earlier also, n is equal 1 by n, sorry, 1 by n, you have to write 1 by n. Here, xi I is equal to 1 to n. Let's erase this. Let's erase this, fine. Now, having understood what mean is, so what is mean telling us? Mean is telling us about central tendency. Mean is telling us about central tendency. Fine. So if you want to think about it, mean tells us what is the average petal length for Setosa, for Virginica, and versicolor. This is what means tell us. That is, mean measures the central tendency. No, there is another concept like mean measures. Let me write it here. Mean measures the central tendency. Now, there is another concept just like mean. As I told you right now, there is something called a spread. So there is something called spread. S-P-R-E-A-D. Fine. So let's understand what spread means intuitively and graphically before we go and write the mathematical equation for it. So let's see. So for understanding the spread, I have just opened this graph, which we have this PDF, which we have plotted earlier. So here, if you look at these plots, your mean for Setosa was like 1.4. It is somewhere here, 1.4. This is the mean for what the mean for this versicolor and Virginica are here. So for it's about 4.5. The mean for versicolor is around 4.5. It's something here around here. It's like 4.5, 4.5. And for Virginica, it's around 5.2. So let's say it is somewhere around here, 5.2. 5.2. Fine. So this is the mean for Setosa. This point is the mean for versicolor, and this point is the mean for Virginica. Now, I'm just putting these numbers roughly. They are not the exact means, but the problem here is, if you notice, the range of Setosa flowers width is, if you can see this width, the range of Setosa flower width is much thinner than the range that you have for either versicolor. This is, let's say, the range for versicolor. This is, you say, the range for versicolor, and this is, you, let's say, the range for Virginica. So the range of Setosa flowers petal width is much thinner than the range that you have for either for versicolor or for virginica. So if you look at these histograms, or let's say this PDF, then width here basically represents your spread. This width here represents your spread. spread, spread. This width here is basically representing your spread. Fine. So spread basically means what is a typical range or how widely my PDFs are spread, or let's say if there is a histogram, how widely my histograms are spread. So if I can somehow measure this spread, right, I know what is the central tendency. If I can also measure this spread, it will give me a good intuition on how wide these points are spread. So if I know that the spread is small, that's very useful because I know that most of my points are around 1.4. If I know that the spread is wide, for example, let's look at this or this. Let's assume. So here this spread is large. Here the spread is very small. So let's do one thing. Let's assume my spread is here in case of Setosa flowers. In case of my Setosa flower, let's assume my spread is 0.5. This is the assumption that my spread is 0.5 in case of Setosa flower. So it means that most of my points, if my spread is 0.5, so if I subtract, this is 1.4, let's say. If I add 0.5 in 1.5, 1.4 plus 0.5, let's say, and here 1.4 minus 0.5. So what I am getting here, I will get 0.9. Here I am getting 1.4, and here I am getting 1.9. So it will be something like this is 1, so 0.9 will be somewhere here, and 1.9 will be somewhere here. Let's say, let's suppose this is 1.9, and my central point is 1.4. This is 1.4. So you understand that if I just add a spread to it, I know most of my points lies between 0.9 and 1.9. That it means here in case of Setosa flowers. Now let's assume for this, let's say for 4.5. Let's say, so let's assume that for this spread, that is for versicolor, the spread is 2. Let's assume that for versicolor, my spread is 2. Just assume that. So even though my mean is 4.5, if this spread is 2, I know that they typically lie between 2.5 and 6.5. Why 2.5 and 6.5? If I will add, this is 4.5. If I will add 2 inside this plus 2, I will get 6.5. If I subtract minus 2 from it, so I will get 2.5. So for versicolor, my spread is between 2.5 to 6.5. So this is the typically it lies between 2.5 and 6.5. One important thing is, this doesn't mean that there are no points outside this 6.5. It is just a measure of how widely spread your distributions are. That is how widely spread most of your points are. There may be some points which lies beyond 6.5 and which lies before 2.5. But most of my distributions are lying in this range. This means that. So imagine if I have to understand about distribution without plotting. Remember, all your computer plotting tools are only 40 to 50 years old. Prior to that, you didn't have tools to plot like this. People used to plot with hand. So instead of plotting, they are using the numerical approaches which can help me understand the spread. So what they are using? They were using numerical approaches. Before this tool was developed, plotting tools was developed. So here we are seeing the plot and we are saying, okay, your Virginica is much widely spread. And of course, your Virginica is much more widely spread than your versicolor. Your versicolor has a much wider spread than your Setosa. This, we are looking at it from a plot and saying this. Imagine if you didn't have a plot and we wanted to get some numerical representation of spread. So what I have used as a spread can be thought of as a variance. So let's understand what variance is. So there is something called variance of a, so there is something called variance of a bunch of numbers. So let me do one thing. To understand the variance, let's erase this. So let's take So let's understand what variance is. So for understanding the variance, let's take our set of petal lengths. So we have, let's say, we have already seen this petal length and we have petal length x1, x2, x3, so on till x50, right? We know this. And after that, we said that our mu or the mean is nothing but the summation of all these values. So basically, what we are by mean? Mu is equal to summation of I is equal to 1 to n xi multiply 1 by n. Where n was where the value of n is equal to 50. I know this. Fine. So this is my mu for calculating the mean. So what is spread? Spread basically says how far are my points typically from the mean. Spread basically says how far my points are typically from the mean. So variance is often defined as summation across all points. Let's suppose we have, let's say we have some points like some points like here. We have some points here, let's say, where my points are, let's say here, this point is x2. This is my, let's say, x1 points. Let's say this is my x3 points. This is my x3. And let's suppose this is my mu. Fine. That is my central value or mean. This is my mean. So what is spread? Spread is basically how far my points typically are from the mean. That is, this is my mean value. And these are, let's say, my observations. X1 till, let's say, x50. I'm taking here only 3 observations just to make you understand. So how this observation, how far this observation is from this mean? How far this observation x3 is from this mean? How far this observation x2 is from the mean? Now, how the variance is defined? Variance is basically defined as, let's define the variance. Variance is basically defined VAR is equal to summation of across all points, summation across all points, that is I is equal to 1 till I is equal to, let's say 50, here 50 observation, xi minus mu whole square, here 1 by n. So this is my variance. So what actually I'm doing here, I'm taking each of my points as xi, and I'm subtracting each of my points from me, right? So what this is telling me is, if my mean, if this is my point, let's say x1, so what is the distance of, this is the distance, this is the distance of x1 from this mu, and let's say if I subtract xi, for a time being, let's forget this square, let's calculate xi by mu, let's calculate this part, xi minus mu, let's calculate this part. So here, if this is on this number line, this is has a greater value than this mean. So if I subtract xi minus mu, I will get some positive value here. That is, my distance will come out to be positive. And let's say if I subtract this x3 from me, so what it means, let's say if this value is coming out to be some negative value, let's suppose this is coming out to be -1. The distance between, if I subtract x3 minus mu, let's say this is minus, let's suppose. Fine. So it can be the distance, this distance can be xi minus mu, this distance can either be positive or this distance can either be negative. You have seen this. Maybe this distance can, some distance can be negative, some distance can be positive. It will be like that. And this is my, so we understood this is x1, this is x2, and this is x3. So, but we want to measure the distances, but it is coming out to negative. So that's why what we are doing, we are just squaring it so that all these numbers, that's why we are just squaring it here so that all my numbers could be positive, so that we will get all positive values, right? Now variance basically is defined as summation over this sigma over each of the points when you subtract it from the mean and square it. So this is the formula of for variance. Intuitively, let's see what it is doing. It's basically saying what is the distance of each of my points from the mean, right? Of course, what is the square distance? This is my, let me take some other color. So this is my basically square distance. This is basically my square distance. If I can just, if I can, now what I can do quickly is, what if I can take this square root of variance? Simply, if I will do the square root of variance, so what I have to do? I have to simply do square root here, square root here. I have to add the square root inside this. So if I will do the square root of variance, what I will get? I will get standard deviation. Standard deviation. So let me write here, square root of variance is nothing but this is STD, standard deviation. This is my standard deviation. So this part is my standard deviation. Fine. So let's understand this term. It's basically saying what is the deviation. So what is the average deviation of points from the mean value? This basically is saying average deviation of points from mean. This is telling me this is my standard deviation and it is telling me what is the average deviation of points from the mean value, right? So if your standard deviation is small, you know that the spread is small. The word spread that I used is basically a simple English word, but what I actually mean mathematically is standard deviation, right? So let's look at what is the standard deviation for each of this in the code. So let me write the code for you and let's see, understand this standard deviation with the help of code. So for calculating the standard deviation, what I am doing, I am simply copying this code only. Let's copy this code to be better. Copy and let's paste it here. Only something I need to change here. I'm using numpy, so let's say I have to write instead of this mean, simply I have to write std here. This will calculate the standard deviation. Let's write std here also. Instead of this mean, std here also. Instead of this mean, std. Let's write std here. Fine. Let's the first in the first line, let's add one more print statement. Print standard deviation. Standard. Fine. So this will be good. Now, if I just run this code, let's see what I am getting. I am getting this standard deviation like this. So standard deviation, thankfully, is very simple. So what you get? You get STD. This is STD. And what you can just give it, the standard deviation, np.std. If you are just doing this np.std and giving it, it will give you the standard deviation. Now, here is an important thing. If you look at the standard deviation, so this is again Setosa. This is again Setosa. This is again Setosa. This is again versicolor and this is again Virginica. This Setosa has a much lower standard deviation. This Setosa has a much lower standard deviation, which means that it has a much thinner spread. Much thinner spread. Since it has a much lower standard deviation, it means it has a much thinner spread. Or much lower spread, or you can say much lower spread as well. While your versicolor has a slightly higher, slightly slightly higher spread. This versicolor has slightly higher spread, and this Virginica has even still higher spread than this versicolor. This Virginica has more spread than versicolor color. So I told you earlier, by just looking at mean and standard deviation, and I can quickly come up with some very, very interesting thing for you. So if my mean was 1.46, if my mean was, let's say 1.46, and if my mean was 1.46, and if my standard deviation is 0.17 here, let me if my, let's say, mean is 1.46, and I know my standard deviation for Setosa is 0.17, which means that most of my points lie in the interval of, or at least a good number of points, or a majority of my points. I shouldn't say most here. I will say majority of points lies between an interval of 1.46 to 1.46 minus 0.17 and 1.46, let's say, plus 0.17. So most of my points lies between this interval. And I know most of my points, Setosa flowers, or a large number of my Setosa flowers lie here, right? Similarly, what about my versicolor? My second one is versicolor. This is my versicolor. So I have a variance of standard deviation of, not variance. I have a standard deviation of 0.46 in versicolor. So, which means that most of my points will lie between 4.26 minus 0.46, and this is my 4.26 middle value, and this is my 4.26 plus 0.46, which will come out to be, let's say, this will come out to be 3.8. This is 4.26, and this will come out to be 4.72. So most of my points lies between these intervals. Now, what about the third one, which is Virginica? So it has a standard deviation of 0.54, which I can take it as 0.55. So I know 5.55 is the mean. 5.55 is the mean of this Virginica. So what is the standard, and standard deviation is 0.55. So 0.55 will get subtracted here, and 5.55 plus 0.55 get added here. This will give me the new, this will give me what value? This will come out to be, let's say, 5. This will come out to be 5.55. And this will come out to be, let's say, 6.1. So this is how my intervals are, right? So when you have done, so what you have done now is you have taken the mean, and you are saying the spread is this much. If the spread is wide, it means that the points are widely spread. If the spread is low, they are much more densely grouped. So by just looking at mean and variance, I can imagine that this plot in my head, that's the advantage of mean and variance. Again, in variance or in standard deviation, just one outlier can corrupt the whole number. Just like me, this standard deviation also get, just like mean, this standard deviation also get corrupted by one outliers. So, because at the end of the day, the variance formula is still the same. So, you basically have 1 by n, which is averaging. So, you have xi minus mu square. So, if you have, let's say, one x1 which is very, very far away. If you have one x1 which is very, very far away, its distance from the mu will be very large, because mu is my mean. So its distance from the mean will be very large, which means then there will be one point xi for which the value will be very, very high or very, very large, which means your variance also can be corrupted by one mistake or one outlier or one error. So these things, standard deviation, variance, and mean, these all three things get corrupted by one extreme outliers. So that's all for the today's session. In the next session, we will discuss about median, percentiles, quantiles, IQR, and many more things. Till then, keep smiling, keep learning, and keep commenting. See you in the next session.